Okay. Good. Do you see my screen?
Yes, yes.
Good.
Okay, you see today that the speaker today is Carsten Schneider. He is from Risch. This is the Institute of Bulgarian in Linz in Austria. And his talk, this is multi-summation, indifference links and application. Please, Carsten.
So thanks a lot for the invitation. It's a great pleasure for me to present you my research topics and what I'm mainly interested in. So, okay, here is the outline of my talk. I will start with a warm-up example. Then I would like to give you some more details on the underlying machinery. So this will be more the algebra level. And in the third part, I want to show you applications, how one can use this machinery. So let's look at the following example. You see here a sum. And if you look closer at the summand, you see here, for instance, j factorial, k factorial, and more complicated factorial expressions. And the second term of the summand is again a product of factorials times a linear combination of these guys. And if you have a look how they're defined, it's S sub 1 of n. And with that object, I denote the nth harmonic number. So usually maybe you're more familiar with this notation, h sub n. But in this talk, I will stick to that notion, which is more familiar in the particle physics community. So you see here basically a product of factorials times linear combinations of the chase harmonic numbers, the k plus chase harmonic numbers, and so on. And the summand depends on j, k, and n. And we finally sum this over j and k from 0 to infinity. And actually, this is a problem which arose within my colleagues from particle physics. And the main task now is to simplify that sum. So let me show you how this can be done. Let's denote the summand by f depending on j. And I, in the moment, ignore the extra parameters k and n on which this sequence also depends. So I just focus on the j dependency. And given that expression in j, I look for another expression in g, another expression g depending on j, such that this telescoping equation holds. So in this particular instance, my summation package sigma in Mathematica that can deal with such objects finds that expression. And you see it's again an expression in terms of factorials and a linear combination of harmonic numbers. By the way, you can plug in this g into the telescoping equation, and then by simple polynomial arithmetic, you can verify correctness. So on this level, one can ensure, so one doesn't have to know how the algorithms work. You just take the result and verify it independently of the algorithms that it's correct. Well, what have we gained if this g works on the summand level? We sum now this equation over j from 0 to a. So a truncated version basically of, so a finite version. And then on the left-hand side, we obtain here a truncated sum, which basically is that sum, except that we don't sum to infinity, but only to a truncated version. And on the right-hand side, if you sum this over j from 0 to a, then by the telescoping trick, all terms vanish incrementally, and what remains is the evaluation at the upper bound plus 1 minus the lower bound. So what you basically see here is the discrete version of indefinite integration. Well, you can now plug in the particular found g. And if we do so, we see that the truncated version of the first sum here equals to that expression. And finally, we send a to infinity, so that really this sum here matches with that sum where a is sent to infinity. And knowing that the harmonic numbers behaves like the log function, one can easily see, and actually one can check this computers by computer algebra algorithms, one can find out that this expression and that expression, which depends on A, vanish. So what remains is only that expression which is free of A. Okay, so this first sum can be simplified to that expression which can be given purely in the harmonic numbers of k, n, and n plus k. Now let's turn to the second summation quantifier. So let's put it on top. But before so, let me just maybe indicate how this works. You load the summation package sigma into Mathematica that I have developed the last 20 years. Then you define your summation object, the truncated version, into Mathematica. And then you apply the command sigma reduce to that object, and you obtain the result that I have explained to you earlier. And then I have also a command sigma limit, which then performs the limit calculation. And actually behind I have series expansions, which are again symbolic algorithms that can be handled nicely. And one can deal completely algorithmically with this limit calculations. Yeah, and that's finally the result. Okay, so we have obtained that. And now, as I already wanted to mention, let's apply the second summation quantifier. Here, there's a subtle point. Actually, the sum starts at k equals 0, but here at k equals 0, I have a pole. So in the moment, I cannot deal with the full summation problem, but I have to start with this updated lower bound to at least start with a correct problem. And I can repeat the game. Let's denote the summand by f. And this time it depends on the summation variable k. And I'm looking again for an expression g such that this telescoping equation holds. In this particular instance, I fail. There is no nice solution. So what can we do? Well, we now utilize the extra fact that the summand also depends on an extra discrete parameter n. So let's sneak in this extra dependency that f actually also depends on n, and we look for a g which also depends on n. And well, just this insight will not bring you any further advantages, but now we use the fact that we not only look for a telescoping equation for our original summand, but we shift the summand also in n. So we replace n by n plus 1 in the summand. So you have here the summand, and you have here the summand shifted by n. And now I look for a linear combination of the summand and the shifted summand such that we find a telescoping solution. And in this particular instance, we find a solution, namely C0, which is minus n, and a C1, which is equal to n plus 2, and this expression here. By the way, you can plug in that solution into this so-called creative telescoping equation, which originally has been introduced by Dor and Zeilberger. And you can again verify correctness by simple polynomial or rational function arithmetic. So on the summand level, we can verify the correctness without knowing anything about the algorithm, how it works. It might be a black box method, but having the result, we can verify it nicely. This is also called in computer algebra a proof certificate, that one can certify the correctness without taking care how the algorithm actually worked. And what is very important in the ansatz is that C0 and C1, these two expressions are free of k. So they are constants with respect to the summation variable. Otherwise, you will, if you allow also a k dependence on the constants, you would always find a solution trivially by linear algebra. But if C0 and C1 are not allowed to depend on k, it's not so easy to find a solution. But the more shifts you do, the higher the chances are. In this particular instance, we only shifted once in n, and we were already successful. What have we gained? Well, now we sum this equation as in the previous case over k from 0 to n. Then on the left-hand side, all terms vanish except at the upper bound plus 1 minus the lower bound. This is again the telescoping trick. And on the right-hand side, we sum over this from k from 1 to a, and we get this nasty expression. Well, this is just telescoping, except that we have here the shifted version of the summand. But now, by linearity, we can split the sum. And this is now the crucial point. The constants C0 and C1 are free of the summation variable, so we can pull it out. And now observe that sum that you see here is exactly our input sum. And that sum here that you see here is again the sum, but n is shifted by n plus 1. What we have gained basically now is a linear recurrence of order 1. So we have the sum and the shifted sum equals this expression. And plugging in g explicitly yields this linear recurrence. And finally, we send again a to infinity. Please note on the right-hand side, there is no a dependency. So only here we have to perform the limit. And doing the same trick as you have seen earlier, that one sees that the harmonic numbers behave like the log, one in the end obtains that first order recurrence, which is inhomogeneous. Next, we solve the recurrence. And in this case, we find, which is another tool of the summation package sigma. In this particular instance, we find one particular solution of the recurrence and a homogeneous solution. And similar to linear differential equations, it's the following. If you have a linear recurrence of order m, and you find m linearly independent solutions of the homogeneous version and one particular solution, the recurrence is completely solved. And in this particular case, we have a recurrence of order 1. So one homogeneous solution and one particular solution is sufficient. So our original sum, which by construction is a solution of the recurrence, must live in the solution space. So looking at one special case, for instance, n equals 1, finally tells us that we have to choose c equals to 0, and we have obtained this closed form. And please note, let me mention that one can again easily verify that this solution here, that this expression indeed is a solution. So one can verify by simple polynomial arithmetic that that is a solution. This is a solution by construction, where we have used the proof certificate on that level. As I mentioned here, this is the proof certificate, which allows us to verify that we found indeed a correct recurrence. So all these steps can be verified. So we know both sides are a solution of the recurrence. We know that they agree for the first initial value. Therefore, they must agree for all values. So we are not only have found a simplified version, but we have also a proof that the right-hand side evaluates the same as the left-hand side. So this can be done again with the summation package sigma. I load in this sum. I compute a recurrence by using the command generate recurrence. This is a recurrence that you have seen earlier. Next, I perform the limit. This is again a function by sigma, which performs the limit when we send a to infinity. Next, we solve the recurrence with the command solve recurrence. In this particular instance, you see here the homogeneous version, which is indicated by the 0. And you find a particular solution, which is indicated by the 1. And finally, I have the command find linear combination, again, a command from sigma where we take the solutions. I give as insert as problem the boundary conditions, and then I find here the closed form. So in other words, this ugly sum evaluates to that expression. And now I only have to take care of k equals 0, which is still missing, which is another round of symbolic summation, which I want to skip. And in the end, this quite heavy sum simplifies to the harmonic numbers of first kind and the harmonic numbers of second kind. Okay. Are there questions so far, or is that clear? You can always ask questions if something is unclear. No? Then let's continue to part 2. I want to give some more details how this machinery works. And let me summarize first the basic tools. So we are given a definite sum, so where the summand itself can be any expression in terms of indefinite nested sums and products, or it can be a hypergeometric expressions. There can be the harmonic numbers involved, but there can be more complicated nested sums involved. And then we sum this over k from 0 to n. So this would be a definite sum, where n you see here, and it also depends in the summand. Or instead of n, you can have here also infinity. This would be for me also a definite sum. And given such a definite sum, and where the summation bounds strongly depend on the output, we look for a recurrence. This is based on Dorn Zeilberger's creative telescoping paradigm. Zeilberger himself introduced an algorithm if f is a hypergeometric term. And in this machinery that I work, this is highly generalized for indefinite nested sums and products that you will see later a bit more. So if I am successful to find a recurrence, then I have a rather general recurrence solver, where the recurrence can look like as follows. So it's a recurrence of order d. D can be, for instance, 1, as you have seen in the example. It can be 2, 3, 4. And the largest cases that I have dealt with was maybe d equals 45. So a recurrence of order 45. And the coefficients itself, they can be, in the right-hand side, they can be given in terms of indefinite nested sums and products. And given such a recurrence, one can decide algorithmically and can find all solutions which are expressible again in terms of indefinite nested sums and products. So let me show you two other examples. So here you see, for instance, a recurrence which is of order 2. You see an plus 1, and an plus 2. And the coefficients depend on n and n factorial. So in a non-trivial way. And using the summation package sigma, I find two linearly independent solutions of this homogeneous version, namely a product over the factorial. And here you see basically a sum over the factorial and a product over the factorial. So these are for me indefinite nested sums and products, where you see, for instance, here the n, which pops up here, but will not pop up anymore inside. So it's indefinite nested. And this basically gives you the full solution space. Or here you see another recurrence where the coefficients are given in terms of the harmonic numbers. So a recurrence where the coefficients are described by harmonic numbers. And in this case, it's again a recurrence of order 2, homogeneous. And I find here two linearly independent solutions where you see here products over the harmonic numbers as solutions. So this is a rather general solver. And if I find sufficiently many solutions, I can try to combine the solutions to find an alternative expression where the solutions are indefinite nested. And that's the crucial point. I start with something which is definite, where n pops up at the upper bound and inside. And I will construct solution, a representation, where the n occurs only outside, but not anymore inside. Let me demonstrate that on another example. You see here basically a triple sum, where the summand itself is given again in terms of factorials. And let's demonstrate the machinery, how it works for the sum. And as you have seen in the previous example, in the warm-up example, I first look at the inner sum. And now I try to compute a recurrence with respect to the next summation variable, which is r. I compute a recurrence with respect to r. I solve the recurrence with respect to r. And then I obtain this solution, which is a linear combination of two hypergeometric expressions. So in other words, I have simplified the triple sum to a double sum. By the way, finding this identity, this is summation technology from the last century, more or less the book A equals B by Petkovšek, Zeilberger, and Wilf. This is a technology where you could already deal with that sum. Now let's look at the next sum. It's again basically a hypergeometric sum, except that we have here now two different hypergeometric terms. And let's compute again a recurrence now with respect to the next summation variable, which is j. I compute the recurrence with respect to j. I solve the recurrence with respect to j, and then I combine the solutions, and I find this alternative representation. In this case, you find here again hypergeometric product, so factorials. And in addition, you see here an indefinite nested sum with respect to j. You see the j here, but the j does not arise anymore inside. Whereas the original problem, you see the j here, the def bound, but also inside. So this is a highly coupled definite sum, whereas here the j is pulled out. It's a decoupled problem. Okay, you might say it's not a simplification because this box, the input box, has a similar size like the output box. But for me, it's a real improvement because the j pops up not in the summand, but only outside. Let's plug it into the sum, and now I have to deal with that sum. And now the important thing is,
I have a question.
Yeah.
The previous slide. What about? Oh, I see. I'm sorry. I just didn't see something. So please continue.
Yeah. So the important thing once more is that the j here is now only outside, and now I replace this box by that box, and now I sum over j from 0 to n-2. And now the important thing is that this summand is again an indefinite nested product sum expression where the j will not arise inside. And I can now apply again my machinery because this fits into, I tailored the summand in such a way that it fits to my input class of the algorithms. So I can now compute again a recurrence with respect to n. I solve the recurrence, I combine the solutions, and in the end, I obtain that simplification in terms of the harmonic numbers of second kind, and S sub S minus 2 means that I have here also the alternating sign involved. And this is now a clear simplification. This triple sum can be simplified just by the harmonic numbers of first, second kind, and this alternating sign variation. Okay, this is basically the toolbox in action. Now so here is basically again the simple example how this can be done with Mathematica. You load in the summation package sigma, you load in the harmonic sums package by a former colleague of mine who worked with limit calculations, who can deal with limits nicely, and you load in the package evaluate multisums, which is a package which uses these two packages and automatizes all the tools. So if you just input this sum into Mathematica, and now you execute evaluate multisum, then all the tools of sigma and harmonic sums are used: recurrence solving, finding recurrences, telescoping, taking limits, and all this is done automatically. And in about 1 minute, you will find this output. And it's basically completely mechanized to simplify such sums and to express it in terms of such indefinite nested sums. Now I would like to give you even some more details. Let's zoom in more to explain a bit more how this machinery works. And for that, let's look at an even simpler example. We just want to sum over the case harmonic numbers. So here I have the case harmonic numbers, and I want to sum over k from 0 to the upper bound. Okay, how is this working in the summation package sigma? So the main idea is that all aspects of sequences are translated to a formal setting, namely to in computer algebra, I personally and all others prefer to work in polynomial rings or in rational function fields. So let's design a formal ring. And we start basically with this rational function field, which are basically fractions of polynomials in x in the numerator and denominator. And then I join a new variable and I consider this polynomial ring. And basically in this formal ring, I want to solve the problem. So, well, these are just variables. It's now basically the algebraic setting. And now I have to interpret the variables. So what I do first is that I construct an evaluation function, which interprets the variables as sequences. And let's start with the rational functions. So let's take a rational function, p divided by q. P and q are polynomials. And I want to evaluate it at a point n. And it's just naturally, we just evaluate the polynomial at p at x equals n, and we evaluate q, where we replace x by n and obtain this rational number, provided that there's no pole in the denominator. If there's a pole, we have a problem. And in this case, basically, I would allow any point evaluation. For simplicity, let's say, if there's a pole, I will always say I evaluate to 0. It could be also 1 if you prefer, or it could be 5, or you could introduce a new symbol even to indicate that, but then we leave the rational numbers, and I don't want this. So let's just say if there's a pole, let's map it to 0, and if there's no pole, I evaluate this rational function by replacing x by n. So this is the evaluation function for any expression which depends only on x. Now, I want, as I said, S should represent the harmonic numbers. So it's most naturally to say, if I want to evaluate S at a point n, the evaluation function basically just should map it to the nth harmonic numbers. So S evaluation of S, comma 2 would be 1 plus 1/2, which is 3/2. Okay. And now, knowing how S should be reinterpreted as an evaluation at a certain point, I can now also say how a polynomial is evaluated. Namely, I take a polynomial where it's of degree d in the variable s, and the coefficients of the polynomial are rational functions in qx. And well, I just evaluate it by applying the evaluation like a homomorphism on each of the expressions. So I know how to evaluate the coefficients because this I have defined earlier. So I just evaluate the rational functions. And whenever I see an S, I just replace it by the nth harmonic numbers. And this ring, together with the evaluation function, I call in the following an eval ring. Okay. Unfortunately, the name evaluation ring already exists, so one must be a little bit careful, but this is only an internal construction. So basically, whenever you have an expression in this polynomial, in this formal ring, and you say, I want to interpret it as a sequence, you apply this evaluation map and you get the sequence interpretation. It's something like an interpreter. You have a formal object, and then you apply the eval function, and then you say, this is the number behind. Okay. And yeah, as I said, this evaluation function allows us to map to sequences, namely take our formal ring. Now we can map it to sequences by just taking the element and evaluate it at n equals 1, 0, 1, 2, 3, 4, and we get a sequence. So we have now a connection between this formal ring that you see here and the ring of sequences. And this tau is almost a ring homomorphism. So let's look at that. I apply tau to x, which is basically the evaluation at x at 0, 1, 2, 3. So I get just that sequence. And I execute tau at 1 over x. At x equals 0, I have a pole. And if there's a pole, I just map it to 0. And then I have here 1, 1/2, 1/3, 1/4, and so on. So I get basically two sequences, tau x and tau of 1 over x. And now I multiply the two sequences. And in the ring of sequences, this is done in this case by the Hadamard product. So I multiply component-wise. This component is multiplied by this component. This component is multiplied by this component, and so on. So I just get back as entries 0, because 0 times 0 is 0. I get here 1, 1, 1, and so on. So this is almost the 1 sequence. And the 1 sequence, this is tau of 1. Tau of 1 gives the 1 sequence. And tau of 1 is tau of x divided by x. And you see now, this would be the property of a ring homomorphism. Applying tau to x and tau to 1 over x should be the same as tau of x times 1 over x. And here, this is almost an identity, except that because of the pole, we have here a problem. So we do a trick now, which you see maybe more often in the sequence world, in the summation world. We say that two sequences are considered as the same if they agree from a certain point on. So for instance, this is an equivalence relation. And you see here, these two sequences agree from the certain point on, namely exactly only at the first point they are wrong, and from all other points on, the sequences are the same. So these two sequences live in the same equivalence class. And now we go to the quotient ring. And in the quotient ring, these two sequences are actually the same. And by using this trick, we basically now obtain a ring homomorphism. Tau is a ring homomorphism and maps and basically reflects all the properties that we want. Okay, even more is the case is true, namely this map from the ring, the formal ring in the variable x and s into this sequence where we factor out the equivalence classes, this equivalence relation, and this is an injective ring homomorphism. So what we obtain is a ring embedding. Okay, and well, this is the evaluation function. And the last thing what we do is that we construct a ring automorphism in order to model the shift behavior. Because you see, I want to deal with a telescoping problem, and therefore I have to shift objects. Well, if we want to shift the rational functions, it's clear we replace x by x plus 1. This is a natural shift operation. And well, if we shift the nth harmonic numbers, we just change the upper bound of the harmonic numbers. And by updating, we get the harmonic numbers back plus 1 over n plus 1. So if we shift the harmonic numbers, we can write it as a harmonic numbers plus 1 over n plus 1. So it's naturally, if we want to shift the variable s, that we should map it to s plus 1 over x plus 1. And well, with that, we know basically how the shift operator should act on this formal ring. Namely, we take again such a polynomial of degree d. And if we want to shift it, we just apply the automorphism. It should be an automorphism. We apply it on each of the terms. We zoom in. So whenever we see a coefficient which depends only on this rational function field, we use this definition sigma prime. And otherwise, we use this definition. And what we have constructed here now is basically a ring together with an automorphism sigma, which is also called a difference ring. And what is important is, so basically we can now model in this formal ring the shift behavior. What will be important later is the set of constants. These are all elements which are kept invariant. This is an extra ingredient. So far we have the formal ring, we have the evaluation function, and we have this shift operator, this ring automorphism. And an extra ingredient, what we need is the set of constants. These are all elements which are kept invariant with respect to the automorphism. So these are elements which are kept constant. And it's easy to see if you are given a ring that this forms a subring of A. And in my world, I will always take care that the constants remain a field. So that's the reason why one also calls this the constant field. Okay. So in this example, in our concrete example, the set of constants are just the rational numbers. This means whenever you take an element and it's kept invariant, it cannot depend on the variable x, and it cannot depend on the variable s. So one has to do something to see this. I don't want to prove this, but it's a fact. The constants are only the rational numbers. And this is a special case what I call an R pi sigma ring. You will see later the definition, what I mean with that, which has originally introduced by Michael Karr from 81. And I built my whole theory on difference rings or fields where the constants remain unchanged. This is an important ingredient. So let me summarize. We have a formal ring. We have an evaluation function which allows us to interpret the objects as sequences. And we have a ring automorphism which allows us to model the shift behavior within this formal ring. And now the important thing is that the evaluation function and sigma, they interact. This means if you first shift the variable and then you evaluate it at the point, then this is the same as you evaluate it at n+1. So you can basically, instead of first shifting and then evaluating, you can evaluate at n+1. So they fit nicely together. And if we turn this now to our ring embedding, this injective ring homomorphism, it means the following. We first shift formally, and then we interpret it as sequence. That's the same as we first interpret it as sequence and then shift the sequence. So in other words, we obtain an injective difference ring homomorphism. We can shift formally by just shifting the variables, or we can interpret it as sequence and shift in the sequence. And it's an injective difference homomorphism because this diagram commutes. So going this way or going this way, we get the same evaluation. We come to the same sequence. Okay. And since this is an injective thing, it's important. We can completely work formally, or we can work on this level and we do the same thing. So in other words, this is how the sigma works. My summation package works in this formal difference ring where I just act the automorphism on variables. But using this map to the ring of sequences, I obtain here the rational sequences and I join it with the harmonic numbers. And I shift here by shifting the sequences. And there's a one-to-one correspondence between this formal world and this analysis world. And of course, if you want to calculate, you prefer to work with variables because these are finite objects, and you don't work with sequences which are infinite objects. This is always the strength of computer algebra, that you turn an infinite object to a finite representation and work here. But let me stress this point once more. Very often in computer algebra, you have an infinite object. You model your object by variables, and very often you're not sure if you do the right approximation. You say, if I have a solution here, I obtain a solution here. But it's not clear if this is a one-to-one correspondence. In this world where I apply my tools, I have really a one-to-one correspondence. This formal world models exactly the sequence world. And this is a very, very strong statement. In particular, if I want to find a solution here, I obtain it if and only if I look for a solution here. So let's apply that to our summation problem. You see, I want to sum the case harmonic numbers. So this is basically like in the warm-up example. I'm giving here the summand, which I denote by F, and I'm looking for a sequence G in this sequence domain, such that the telescoping equation holds. This is basically a formulation in the sequence setting, the analysis part. And since we have here one-to-one correspondence, I can also go to my formal ring. Namely, this finding a solution here is equivalent to find a solution G in this ring, such that this telescoping equation holds purely formally. In this case, now I find a solution in the variables x and s, so namely x times s minus x. This is the solution in this formal ring. And now I use basically my tau, or my evaluation function, to reinterpret this formal object as a sequence object. And finally, I plug it into that, and I obtain this closed form. Okay. Now, my question is, how much time can I still have to present my talk? How many minutes do you give me?
Well, no less than 15 minutes.
15 minutes. Okay.
15.
Then I will speed up. So I don't want to give too much details. But basically, this is a formal thing. You have seen already here the rational function field where I start the modeling. And then I can join more and more variables, where, for instance, P1 stands for hypergeometric expression. So where the A1, the multiplicand, can be in this rational function field. For instance, A1 could be x plus 1. Then this would be basically the factorials. But it can be any rational function. And I can have basically a nested object. So if I shift P2, then this is A2 times P2. So I have nested objects. Another ingredient is that I allow, for instance, the alternating sign. And using the alternating sign, this is subtle because now I basically introduce zero divisors. I don't want to say more details, but from that level on, I basically work not anymore in integral domains, in rings where I don't have zero divisors, but now from that point on, zero divisors might pop up. And on top of that, I can have sums, like the summand here might be, for instance, a harmonic numbers. This could be, for instance, F1 could be 1 over x plus 1. But more generally, it can be any element in the ring below. So it can be indefinite nested sums and products. And the nice thing is, whenever you give me an expression in terms of indefinite nested sums and products, I can join the variables in such a way that the constants remain unchanged. This means whenever I take an element in this ring and it's kept invariant, then it cannot depend on x. It does not depend on P1. It does not depend on P2. It just depends on the ground field from which I started. So this is a very careful construction that I have to do. But if I do this, I can solve the telescoping problem. And I can do it very strongly in the following sense, namely do such a construction where the constants remain unchanged and take such a very general ring with an automorphism, which describes the shifts of nested products and nested sums. Then I have the following statement. The constants remain unchanged if and only if the difference ring is simple. So this is now pure algebra, I agree. Namely, this means whenever you take an ideal which is closed under the automorphism, then this is only the zero ideal or the ring itself. Or this is also equivalent that we can indeed construct an embedding from the ring into the ring of sequences. So this is a very strong statement. And this is basically the algebra heart. I do rings construction such that the constant field is not extended. And then I can guarantee that my evaluation function that I construct is injective. So now let me stop that and let's turn back more to concrete things. And the first aspect is, if you give me an expression in terms of indefinite nested sums and products and I apply sigma reduce, which you have seen earlier, then I obtain a new expression, a simplified expression, such that A equals B, and such that the objects that we find here are basically sums and products which have no relations among each other. They are algebraic independent. And this comes from the fact that these are basically these generators. They are generators which have no relations. And I can guarantee by this embedding that indeed there is no relation in the sequence word. Okay, so I can construct representations in the output where the sums and products that you see have no relations among each other. And application one is the output is usually much simpler because all redundancy is gone. Application two are basically that I have a canonical simplification. So for instance, I have an expression A1 and A2, and I would like to know, do the two expressions agree? what I do is I apply sigma reduce simultaneously in one common difference ring, and I obtain two expressions, B1 and B2, such that the evaluation is the same. And then I have the following statement. B1 equals to B2 as evaluation, if and only if B1 equals B2 syntactically. So I have I simplify with sigma reduce in a polynomial ring. And if the two elements are the same in this polynomial ring, this is the case if and only if the two expressions evaluate to the same sequence. So I can decide if A1 equals A2 as sequences by reducing to B1 and B2 and compare if they're syntactically equal in my formal difference ring. And in particular, I have a zero recognition that I can check a sequence is zero if and only if in my simplified representation, I obtain the zero sequence or the zero expression. Okay, and basically all these tools work in this optimal representation that I construct difference rings where I have a one-to-one correspondence between the variables and the sequences. In particular, I have canonical representations and the sequence is zero if and only if the expression is zero. Now, finally, I would like to show you some examples. And the first application comes from number theory. And this was an example by Doron Zeiberger that was sent to me. And actually, it's a problem from, so Doron Zeiberger wrote me the following email. Robin and Herb, I'm willing to bet that Carsten Schneider's Sigma package for handling sums with harmonic numbers, among others, can do it in a jiffy. I'm CCing this to Carsten. Carsten, please do it. And CC the answer to me, Doron. If you get such an email, you have two options. You either delete the email because you say, this is rubbish, I don't want to look at it. Or you see that the email comes from Doron, who is a big shot, and it's sent also to Herb Wilf, which is and Robin Pimentel, which are both very well known. So unfortunately, Herb Wilf already died in the combinatorics. So he was a big shot in the combinatorics world. Robin Pimentel is well known in asymptotics and generating functions. So of course I was eager to solve the problem. So I looked at it, and here was the email from Robin Pimentel, Herb Doron. I have a sum that when I evaluate numerically looks suspiciously like it comes out to exactly 1. Is there a way I can automatically decide this? The sum may be written in many ways, but one is as follows. You see here basically a sum like in the warm-up example. We sum k from 1 to infinity, we sum j from 1 to infinity, and you see here the harmonic numbers. So let's apply the toolbox that you have seen earlier. I start with the inner sum. I compute the recurrence. I solve the recurrence and find two linearly independent solutions of the recurrence. And finally, I look at the first initial value, the first two initial values, and I find out C1 is 0 and C2 is theta 2, where theta stands for the Riemann theta function. Okay, so in other words, the first sum simplifies to that expression. Now I apply the second sum, and just carrying this out by telescoping and other tools and limit calculations, one in the end obtains an expression in terms of theta 2, theta 3, and theta 5, which is very close to 1, but actually it's not 1. Okay. Another example by Vadim Zudelin I want to skip. I want to show another example which comes from combinatorics. This was an example that was joint work with Peter Paule and George Andrews. And here you see basically a plane partition. What is a plane partition? It's an array. In this case, n equals 3 means it's a 3 times 3 array. And it's filled with integers where whenever you go to the right or whenever you go down, the integers remain the same or decrease. So this is a plane partition because we have a 3, 2, 1, 2, 1, 0. This fulfills the properties. You can draw such a plane partition also in 3 dimensions. So the 3 means we put here 2 boxes on top. The 2 means we put 2 boxes on top, and the 1 means we put 1 box, and 0 means no box. So we get this 3-dimensional object. Okay, and now a totally symmetric plane partition is such a plane partition when you rotate this image and you also mirror it in any possible way, that you always get the same picture back. This is a totally symmetric plane partition. So you could, in former times, I gave talks with slides where you could now really rotate nicely with the slide, or you could also mirror the slide and you would see the same picture. And George Andrews and MacDonald and Stanley in the 80s conjectured that the number of such totally symmetric plane partitions of size n, this means the arrays have length n, equals that expression. And yeah, finally, 95, Stanbridge, by very smart proofs, techniques, Pfaffians, succeeded in proving this conjecture. But actually, George Andrews in the 90s, earlier, was close to a proof. He used basically determinant evaluations, and he reduced the whole problem to multi-sum identities. But he utterly failed to prove these multi-sum identities. And together with Peter Paule and my summation package sigma, we could handle after a while, after also non-trivial hand manipulations, we could bring it to some representations where we could do it with a computer. So this is basically the first computer-assisted proof. And we could provide an alternative proof using computer algebra. And one of the typical examples is as follows. You see here basically factorials or Pochhammer symbols and basic binomial coefficients. And we have here this non-trivial double sum. And in addition, we use this double sum to define a triple sum. And we use this double sum to define another triple sum. And one of the identities is as follows. The double sum here plus this double sum minus this triple sum minus this other triple sum simplifies to that hypergeometric expression. And we could provide recurrences for each of these guys, and in the end, verify that left-hand side equals right-hand side using the summation package sigma. Okay, so this was basically another result that I wanted to show you. And the last example, I want to show you typical examples from particle physics. So the last 15 years, I have a very strong cooperation with DESI, the Deutsches Elektronensynchrotron, and we are working to simplify Feynman diagrams within 3-loop and now also 4-loop settings. And let me show you one typical example. Here you see, for instance, a Feynman diagram, a 3-loop massive Feynman diagram, which is used to describe the behavior of particles. And I don't want to go into details. Actually, I'm also not the expert to talk too much about these Feynman diagrams, but let me say so much. There is a dictionary which allows to go from this visual representation to a complicated integral representation. And so this was also observed by Feynman. And since the 60s, more and more different tools have been developed to simplify now these integrals in order to extract properties. And in the last years, we developed, so let me just show you a typical example. So in some sense, this would be for me a Feynman integral. So we have a discrete parameter n, and we want to integrate this from 0 to 1. I mean, we all know how to integrate that function. That is not too difficult. So it can be a bit more complicated. There might be some poles or artificial poles, but actually there are also poles involved. So we sneak in a dimensional parameter epsilon to catch up the poles. So this is a discrete parameter, which is not a discrete, a continuous parameter, which is small, and which allows us to deal with such poles or artificial poles or real poles. And unfortunately, the integral is more complicated. So for instance, you see here a 6-fold integral. There are also extra discrete parameters involved, and we have to sum over them. And then the integrand looks like that. So you see here many complicated objects where this parameter epsilon is involved to deal with poles. And you have also the Heaviside function involved here. And let me say, on this level, this what you see here is a hyper-exponential expression. There are even computer algebra tools to deal with such integrals. But believe me, this integral is too complicated with available tools that we have in the moment. So what we do is, we take now this integral, and by my colleagues from DESI, we can translate these integrals to multiple sums. Usually, the integrals do not simplify too much. Then, if you're lucky, you simplify. If you behave stupidly, if you apply the tools in the wrong way, you get even more nasty expressions and game is over. And if you do it carefully, you get similar complicated expressions. And the big disadvantage now is that we can now use the tools that I have described to you earlier to obtain, and that we can apply, in particular the summation package sigma, to obtain simplified expressions. And let's look, for instance, at that integral. Okay, as I said, this integral is not properly defined. For if you send epsilon to 0, we would have a problem. So basically, one is interested in its Lorentzius expansion. So this is a 3-loop integral. This means by the physics theory, it follows that one will obtain a Lorentzius expansion of order 3. And one is basically interested in the first coefficients up to the constant term. This describes the divergency of the Feynman integral, and one strongly is interested in particular this constant term of this power series, formal Lorentzius expansion. And if you do the techniques from my DESI colleagues, by Mellin-Barnes integrals, binomial theorem, and many other techniques, you can simplify the 6-fold integral to a 6-fold sum, where the summand looks quite familiar to the examples that you have seen earlier. So binomial coefficients, factorials, and the harmonic sums. And now basically I use the tools that you have seen earlier. I work from inside to outside, compute stepwise recurrences, solve the recurrences, combine the solutions. And after about 1 day of completely automatic calculations using the packages that you have seen, you obtain that expression. Now you might say, oh, the input and the output expression are similar sized. But again, please note, this is a completely coupled problem where all the upper bounds, all the variables depend completely nasty. They arise in the summand and in the bounds, and you have no control about the object. Whereas here, you see the nth harmonic numbers. You see the harmonic numbers of second kind. And the most complicated object is an indefinite nested sum where you see the n, which does not pop inside. You see here the I, which does not pop up anymore inside. And you see the J, which does not pop inside. This is an indefinite nested sum. And these are nice objects. They can be nicely explored. We can calculate asymptotic expansions of these objects. We have full control, and we can deal with these objects. So let me summarize. If we go this path to symbolic summation, you obtain expressions which will be used sooner or later at the Large Hadron Collider at CERN. And with my colleagues, we work on that, and we want to basically understand how does the universe look like in the first seconds after the Big Bang. And we want to know if the fundamental forces unite. So my colleagues tell me, by the theory and the experiments that one has, one sees that the 4 forces come close after the Big Bang, but they don't meet in one point. And now the question is, if the theory calculations are refined, do the points come closer or do they stabilize? This would be an indication if the four forces unite or not. And we also want to explore more details about the predicted Higgs boson that has been, which is also called the God particle. Okay, and let me conclude my talk that I developed difference ring machinery for symbolic summation. And actually, there is quite some heavy computer algebra aspect behind. But all these algorithms are motivated and driven always by concrete applications. And I consider the future of computer algebra always in this connection between applications and algebra. So you have problems that you want to solve, and then this inspires you to push forward the computer algebra tools. And you have, of course, you have computer algebra tools, which allows you to be more general, to solve more general and more complicated objects. So there's a nice interaction, and one always has to see it in this interplay between the two worlds. And with that, I would like to conclude my talk.
Okay, thank you very much for the talk. Do you have any questions or comments?
I'm not an expert, but I'm curious about how one integration construct fits in your picture, because you mentioned the analogy with symbolic, with the integration, yes, this telescope. So integration by parts, which as far as I remember is related to abelian identities in some way. Yeah. So do you have some use for that?
There's also something like integration by parts or summation by parts. There's also a tool like this, and it helps for certain applications to do something.
Yeah.
So, but here you see we have a different type of problem. We have a class of input, and for that we can decide, does there exist a telescoping solution in the same domain or in an extension, an appropriate extension. So, and we have a specified input class, and then we can say for a certain output class, we can decide, is there a solution, yes or no? And the algorithms that I describe, they are strongly related to Risch's algorithm in indefinite integration. So one could consider Karr's algorithm already as the Risch version, the discrete Risch version, and I pushed it further to many aspects in the sense. Similarly, solving recurrences, the solver that I have in hands, this is the discrete analog to Michael Singer's very general solver for finding Liouvillean solutions of differential equations with Liouvillean coefficients. So there's also a connection between these two worlds. So there is a connection between the summation world and the integration world, but the algorithms are completely different.
Thank you.
May I ask a question?
Yeah.
Can you use deep learning, neural networks, and so on in your calculations?
No, we haven't used. So in the moment, I mean, I have these tools for a certain input to check if there's a certain output. And then I have evaluate multisums where I try, basically encoded all my knowledge and all my understanding how one could solve it, encoded it basically in the package evaluate multisums so that the user is dispensed by all the details. And basically, it's a tactic how I would basically try to do it. So basically, I try to scope my brain into the package, but there's no deep learning or something in it. Could be maybe used to check things, how the tools could be applied in different ways, and maybe one could improve evaluate multisums by that. But nothing so far has been done.
I had in mind that maybe when you are using the epsilon expansions, then maybe such tools may be useful.
Maybe, when I do expansions, yeah. I don't know, I haven't thought about it. I know that colleagues in particle physics, they start to use also machine learning in a certain level. Then you have also to find integration by parts methods to find differential equations. And here they use also heuristics, and there's machine learning in parts involved.
Thank you.
Do you have some other comments? If not, the next talk will be in commutative algebra. The speaker is from Turkey, and it starts 4 p.m. because the speaker, she's busy before. So 4 p.m. Bulgarian time, the next Friday.
So thanks a lot for the invitation again, and it was a great pleasure to present my work.
Yeah, unfortunately, we cannot offer you a lunch before the talk or after the talk.
Good.